Hello everyone, myself Dr. Vivek MS, Assistant Professor in Department of Chemical Engineering. So today we are going to see small topics on chemical reaction engineering 1. So in last we have discussed about the continuous stirred tank reactor and plug flow reactor. So today we are going to see about the recycle reactor, combination of reactors, size comparison of the reactors. So what is recycle reactor? Recycle reactors are used in the following situations. So first is the reaction is autocatalytic. It is necessary to maintain yield isothermal operation of the reactor. It is necessary to promote a certain selectivity. So let us consider a reactor, that is a recycled reactor, where we are giving as a flow rate of FA0, volume of V0, and a mole fraction of XA0, that is 0. And there is a recycle unit of V3, that is volume 3, and RVF, that is the final product that is recycled, and it is attached to the point K in the initial feed. And it's a plug flow reactor where the reactant enters in FA1 at a feed rate A1, reaction composition at XA1, and volume of V1. Also it exists as a product as XA2, and it is with a volume VF, that is final volume, and XAF is equal to XA2, that is the final product composition of final is equal to composition, that is XA2, which is out of the reactor, that is a plug flow reactor, and capital V is considered as the volume of the reactor, and the point L, that is the recycle point, where R plus 1 into VF is given as a recycle to the initial reactor. So we can calculate the recycled ratio, that is R, is equal to volume of the fluid returned to the reactor inlet divided by volume of the fluid leaving the system. So where is capital R? If it is 0, then it's a plug flow behavior, whereas capital R, when it is goes to the infinity, it is plug flow, mixed flow behavior. The performance equation of the PFR is partially converted, which is given as V by F dash A0 is equal to, with the integral of XA1 to XA2 dXA by minus RE. So finally we will be arriving by solving the integral function, we will be arriving the performance equation unit for the first order reaction as K tau by R plus 1 is equal to ln of CA0 plus R CAF divided by R plus 1 CAF. Whereas for the second order reaction, that is 2A gives a product where epsilon A is equal to 0, the integral form of the equation will be changed into K into tau CA0 divided by R plus 1 is equal to CA0 into CA0 minus CAF, that is initial concentration multiplied with initial concentration minus final concentration divided by final concentration, that is CAF, into CA0 plus recycle into final concentration, that is R into CAF. So this is how the first order and second order equation are derived from the above equations of PFR and MFR equations. That is the final performance equation of the plug flow reactor and mixed flow reactors we take into the consideration for deriving the reactors. So this is the comparison of performance of recycled reactor with plug flow reactor for a first order reaction. So we can check that R value changes from 0 to 0.5, 2, 5, 10, 20 and 50 to a infinity, whereas when R is equal to 0, as discussed earlier, it's a plug flow reactor, whereas when R reaches to infinity, it will be a mixed flow for a first order reaction. So this is how the graph between the final concentration by initial concentration versus tau R by tau P is given. So in this way it is compared, the performance is compared between the recycle and the plug flow reactor. So when we are taking into plug flow versus mixed flow reactor, when there is a no recycle, we can detect from these graphs that is a mixed flow is better for in the first diagram when it is plotted against the mole fraction of final versus 1 by minus RE. Whereas in the second plot, it can see there is a mixed and plug flow are equally good. Whereas in the third graph, you can see plug flow is better. So moving on to the optimum recycle operations, the same performance equation has been taken for from the PFR, that is V by FA0 is equal to tau by CA0 minus R plus 1 in the integration of from R by R plus 1 XAF by XAF dXA minus RA. So this is again integrated further, and the final form of the theorem is by rearranging, that is 1 by minus RA is equal to integration of XAI from XAI to XAF dXA by minus RA, that total division by XAF minus XA. So in this way we can plot the three graphs, that is the correct recycle ratio for the autocatalytic reaction compared with the recycle ratios which are too high and too low. So in this way we can check that recycle is too high in the first graph, whereas the average rate is point of P in the line P, whereas in the second graph we can see there is a recycle just right side of the plot, whereas we can see in the third diagram the recycle is very low compared to the first two. So this from the recycled reactor we can plot this graph. So next, moving on to the topic, design of reactors for single reaction. The factors that to be considered for the reaction selections are type of the reaction, scale of the production, cost of the equipment and operation, stability and flexibility of operation, equipment life, time period over which product is to be manufactured, ease of convertibility of equipment to modify operating conditions or to new unit process, and finally with we have to compare the size comparison of the single reactors. So we are comparing MFR and PFR. We can write the performance equations again, that from the basic rate equation minus RA is equal to KCA power N for the nth order reaction, and we further derive and rearrange that. So we will write the performance equation of the PFR also, and the same rearrangement, and we can finally conclude for first order and second order reactions with this equation number 4 and 5. That is the equation number 4 and 5 are almost similar for both MFR and PFR. So next topic is on reactors for different size in series. So if first we can take different reactors, that is CSTR followed by PFR, that is followed by CSTR. So there will be a graphical representation for the design of this reactor, where initial reactants are given and final output is also being achieved, and we can see there is a difference in rate conversion from the graph, that is x1, x2, x3 are the three different outputs of the reactors at different points, and we can see there is a good mixing at CSTR, then there is a average mixing in PFR, then again a high peak of mixing in MFR. So another topic we can derive by connecting all the CSTRs in a parallel mode. So the final output will be parallelly given, and the volume of the reactor is given as FA0 is equal to XA by minus. So again for a good for a good conversion, we can connect all the PFRs in series. So there will be a higher conversion in PFR, whereas PFRs also can be connected in parallel, which we can compare the CSR conversion, PFR conversion in series with the PFR conversion.